Okay, so we can move to the next speaker. Is Professor Andrea Caiti. Andrea is currently full professor of Systems and Control at the University of Pisa and director of the Department of Information Engineering. From 2001 to 2008, it was the director of the Italian Inter-University Research Center on Integrated System for Marine Environment, and from 2015 to 2017, a director of Centro Piaggio. His research interests include marine robotics, underwater acoustics, and system theory. He is an IEEE fellow, participating to the Control System, Ocean Engineering, and Robotics and Automation Society. So I want to introduce Andrea Caiti, which is presenting his work exactly on underwater localization and navigation for autonomous vehicle. So please, Andrea.
Okay, thanks, Julia, for the very nice introduction. Okay, this is a joint work, actually, that I'm going to present between University of Pisa and University of Florence with my colleagues Benedetto Allotta, Riccardo Costanzi, and Alessandro Ridolfi. And we work together within the framework of the Inter-University Center, ISME, of which Julia talked about in the introduction. ISME actually groups together 9 different universities all around Italy, including, of course, Pisa and Florence, and we are in the Tuscany region of Italy, and this, in a way, helps in collaborating on a daily basis on mutual project. We in ISME we have laboratory facilities in the sea, which is actually a joint laboratory with the Italian Navy, and that is based in La Spezia. So La Spezia is here, Pisa is about 80 kilometers south on the coast, Florence is in the inland, some additional 80 kilometers. So we're close to the facilities, and we have our robots in the facilities, and you will see some videos also of the facility itself. So what this talk will be, at the beginning, I want to make some introduction and give you some motivation and background on what we do for localization and navigation. And after that, I will concentrate on 3 different aspects we are currently investigating. One is that of cooperative navigation. That is navigation when a robot, an autonomous vehicle, is not alone, but there are others, vehicles, surface, underwater, additional platforms, and they all cooperate in the navigation part. The second item will be on payload-based navigation. That is, usually autonomous vehicles are sent underwater for a purpose. So they have a payload. The data from the payload can be used and may be used actually also for localization and navigation purposes. And I'll conclude with just a few examples of tracking systems. So the motivations, well, the motivation for underwater robotics, I think it's possibly evident to the whole audience. Using robots underwater can help in reducing the number of personnel involved. In turn, can increase operational safety. You don't need to put people at sea. It can mitigate the ecological impact. You don't need to have big ships at sea. And all of these help also in reducing the costs of missions at sea that are huge. But one of the problems that underwater vehicles do have, autonomous underwater vehicles do have in their environment is that of localization, to understand where they are. Underwater, you don't have all the facilities that you may have on Earth, in air, to localize yourself. It's a wide GPS denied environment. You cannot use, unless you're going to very short distances, electromagnetic waves. So navigation is still a non-trivial problem in the underwater domain. The trend is going from large single autonomous vehicles, the famous Hugin, possibly the first one that had commercial use at the beginning of this millennium, towards team of robots, team of smaller, more flexible robots that can be underwater, that can be surface autonomous vehicles. There are a lot of plus that I can put down for using teams of small size, low cost vehicles with respect to their larger and older brothers. But there is a minus. That is, with small vehicles, you have low accuracy navigation, while with large vehicles, you have, if not reliable in an absolute sense, but certainly much more reliable navigation systems. Why is that? Essentially because in a large vehicle like the Hugin that has a cost of approximately 2 million euros, you can afford to put a reliable navigation systems, tactical navigation systems. So that's the same navigation systems that you would have with manned submarines. Well, you can put it on board. While with small size, low cost vehicles, then you cannot have you cannot afford the high cost implied by a reliable inertial systems, for instance. So some of the classical navigation schemes that can be implemented also for large vehicles or costly vehicles may not be implemented with small vehicles. Just to briefly review, acoustic positioning systems go from long baseline systems in which you put acoustic beacons. All these are acoustic positioning systems. The long baseline system is the one in which you put acoustic beacons over the domain of navigation, and essentially you do triangulations to localize the vehicles. Short baseline systems still employ acoustic beacons, but with less separations between the beacons, while ultra-short baseline systems use essentially, they use the principle of acoustic arrays to get estimate of range and angle from the reference systems to the vehicle. High-grade inertial navigation systems And are those installed on large vehicles? On large vehicles, you have also Doppler velocity logs. Even Doppler velocity logs can have by themselves a cost that can be compared to the cost of an entire small size vehicles. Okay, something like 20 or 30,000 keys euros. So our idea that our research trend that I'm going to present now goes towards exploiting the possibilities of using low-cost systems in trying to achieve a navigation accuracy equal or at least close to that of larger systems. The first item is that of cooperative navigation. And in this case, we are exploiting a team of vehicles or different assets that communicate with each other through acoustic modems. Now, state-of-the-art acoustic modems have become capable not only of transmitting messages, but also to estimate at least range from the vehicles, from the relative range of the vehicles in communication, and also, in some cases, the direction of arrival. So, putting together range and direction of arrival, acoustic modems have the capabilities, some acoustic modems at least, have the capabilities of ultra-short baseline navigation systems. What can they be used for? Of course, they can be used to get relative positioning between one member of the team with some other member of the team, which is in itself not enough to obtain good navigation capabilities, but you can add to that the information exchange that the members of the team pass to each other. So this is, now I'm going to present some results from the field in a joint experiment we had with CMRE, the NATO Center for Maritime Research and Experimentation. The experiment has been done in deep water. Deep water means that you cannot use Doppler velocity logs, even if available, to estimate or to measure the velocity of the vehicle with respect to the seabed. The goal of the experiment was to estimate the position of an underwater vehicle, so autonomous underwater vehicles, and the sea current velocity in the operating area. What are the available sources of information? Onboard sensors include velocity over water, so velocity with respect to water, heading angle, the information on the sound speed for acoustic transmission, and depth. And from the acoustic network, that is from the other members of the networks, the range and bearing from the other team members, from the other agents, some other nodes position that are communicated through the exchange of information, and its own absolute position through ship-mounted USBL systems. Now, note one thing. This information from the acoustic network is not always available all the time. Otherwise, with the last point, we would have solved the problem. the information come to the vehicle in asynchronous times, and in particular, the own absolute position does not come often. It comes every once in a while. How this is done? Well, each member of the team has implemented on board an extended Kalman filter that is designed with two basic assumptions. One is that the C current is constant in the operative area. The other is that the model of the vehicle is a two-dimensional kinematic model, so you don't change your depth during your mission. The state vector is the absolute position of the AUV and the C current velocity. The input vector is speed over water, course over water, your heading, and of course the additional information that comes from the communication system. You have also other filters running in parallel to the main one, in which you try to track the other assets, the other agents in the network. Now, the filter has to deal with outliers rejection, since most of the communication, information, range and bearing measurement from the network all the information from the network come acoustically, you may have wrong messages, wrong range estimates, wrong bearing due to interference, especially due to multipath phenomena. And this will cause the reception of data that are indeed outliers. The other, and you have to reject them, of course. The other point is that even when you get information from the network, that information is related to a past time with respect to the present time. So there is a latency in the transmission of information and in the gathering of data. And our filters do take into account also this delay in measurements. As I said, not all the measurements regularly, there is irregular sampling, and you have to deal also with this asynchronous arrival of information. So the experiment we did with CMRE was the Dynamic Moongoose cruise 2017. Chief scientist was Kevin LePage. The team was composed by a surface ship, one wave glider, this one, which is an autonomous surface vehicle, two gateway buoys that are autonomous surface assets, and two AUVs, the Ocean Explorers AUVs of CMRE, on which our filters have been implemented. Here I report a result of a mission duration of 4 hours in approximately 130 meters of water. The vehicle was navigating at 8 meters depth. There was no bottom lock with DVL. It is the AUV had a DVL on board, but its depth was such that there was no bottom lock with the DVL, so the DVL was measuring the speed of the vehicle with respect to water, and not to the bottom. And these are the estimated path in the area of operation for the surface ship in red, the gateway buoy almost stationary in pink, and the Grucho AUV in blue. Okay, now we don't have for this experiment a ground truth available. So what we can do is comparing the estimated navigation with respect to the reference navigation that was prescribed to the vehicle. Now, the dive had a duration of approximately 4 hours, 16 kilometers of travel distance, and the error, again, between the estimate and the reference is never over 150 meters throughout the whole mission. A different scheme of navigation, of cooperative navigation that we're exploring presently is actually simpler. That is a method in which we have the gateway buoy, that is what in the previous example was the gateway buoy, is actually a surface vehicle that follows, but it doesn't have to follow strictly the underwater AUV. With a modem, an acoustic modem capable of USBL positioning that stays on the surface vehicle, and the position, the absolute position is of the underwater vehicle is estimated by the vehicle at the surface. The vehicle at the surface, of course, has access to satellite information, and the estimated position, or the measured position, is sent back with a message to the underwater vehicles. The underwater vehicles will receive that with a delay. It may not receive all the messages sent from the surface vehicle, so the underwater vehicles actually implements a Kalman filter, an extended Kalman filter, as the one in the previous explained in the previous experiment. And here it is possible to have a ground truth from the onboard navigation systems, because we did the experiment we did is in shallow water. We use the DVL in this case, not as part of the navigation on board the system, but to acquire data for ground truth. So here you see the navigation from the onboard navigation system in blue. Red is the USBL measurements as received by the underwater vehicle, with some gaps that are due to lack of communication. Here you see the GPS trace of the surface vehicle. So the surface vehicle doesn't need to follow strictly the underwater vehicle. It is sufficient that it stays in the area and it stays within communication range with the vehicle. This experiment that I just described has been extended through a collaboration with Jacobs University of Bremen. Actually, this was part of a European project on sharing research infrastructure. So the C-Lab, the joint laboratories with the Italian Navy that I talked before and that you were seeing in the video, has been used as an infrastructure shared for other applicants, for other research teams throughout Europe to apply for experimentation together with us. You see, we had two surface buoys, two different kind of underwater vehicles. Here you see the control station. People from Jacobs University had implemented in the vehicle the algorithms, however, they could not be present in person in the experimentation due to pandemic limitations. They were in remote connection. And the experiment was carried out with, let me see if I can move. Okay, I may not try it, but essentially, so we had two surface vehicle and two underwater vehicles sharing the same mission. Okay, Filippo and the X300 were underwater, while the gateway buoys, the two vehicles that we still call gateway buoys, were at the surface, gathering information to be shared through the communication network with the underwater vehicle. Okay, just another glimpse for the C-Lab facilities. And one of the things that we were looking at in the mission was also the automatic detection of target. This was done with a side-scan sonar, and this brings to the next part of the presentation, that is payload-based navigation. As you see in the experiment, we use, I mean, the experiment was a navigation experiment, but then the vehicles had a payload to map the bottom with a forward-looking sonar and automatically detect features on the bottom. This is something that is done quite frequently in underwater applications, seabed mapping and exploration. The point is, can we use the payload data to increase the navigation capability of the vehicle? Now, this is a tricky aspect. That is, I've been teaching my students for a long time, do not mix the payload system with the vital vehicle system. That is, the vehicle has to be capable of navigating and coming back home without the use of the payloads. However, it is true that as vehicles become cheaper and smaller in size, and the payload also is not a particularly expensive payload, you may try to use the information from the payload in real time for navigation. And in particular, in the next slides, I will try to show what we have achieved so far in trying to use the forward-looking sonar and the recognition of a feature on the bottom to estimate the velocity of the vehicle with respect to the bottom. That is to use the payload to substitute the Doppler velocity log. Here we have an example. I mean, we're comparing three things. Some model-based approach in which we have a nice dynamical model of the vehicle. And we use that in traditional odometry. And the blue one is when we use the forward-looking sonar as the instrument to measure velocity. And this is the error in estimated navigation during short missions, and at the end you have also the comparison with the GPS at resurfacing. Now, the vehicle had also a DVL system that is not used in the navigation filter, but it is used to compare the results and obtaining ground truth. And you see that the forward-looking sonar-based navigation can compare with the DVL slightly better than the model-based approaches. The model-based approaches give information that is smooth, nice and smooth, but at times inaccurate with respect to DVL. While the forward-looking sonar has some high frequency noise that you can see here with respect to DVL, but indeed is essentially close to the DVL measured systems. The result is that the error in navigation that you make with the forward-looking sonar is definitely smaller than what you may have with a model-based approach. And here you see the ground truth in blue and the resulting navigation with model-based, with an improved model-based, and with the forward-looking sonar. And you see that the forward-looking sonar visually does compare much better than the other two methods. This is the mosaicing of the forward-looking sonar data obtained with the estimated navigation. The part at the right is the same seabed explored in another experiment, and it is used. We have used it to have a ground truth reference also for the sonar mapping. And the scales are not the same, so it's not immediate to look at the same features. But for instance, here, it's the feature that you see here. Okay. Payload-based navigation, this is simulation only for the moment, but where it is possible to use optical systems, that is cameras, we are looking at using the optical system as we did for the forward-looking sonar, that is to measure the velocity with respect to the bottom. And to do so, we need also to use an echo sounder, an altimeter, to adjust the scale factor of the images that you may get with a single camera. Here are the results of our simulation in which the extended Kalman filter based on visual odometry is compared with the same filter based on Doppler velocity log. In both cases, visual odometry and Doppler velocity log to measure the velocity with respect to the bottom. In three scenarios: straight path, spiral path, and a sinusoidal path with increasing speed. In the first two paths, the speed is constant. And you see that in the first two paths, here the error is in meters per second. And you see that we have error below 10 centimeters per second in both cases. With a sinusoidal path and increasing the speed, the error of the system based on the visual odometry is, well, it reaches at the end the 10 centimeters. Of course, I mean, the EKF with DVL is the reference system. So you want to compare your visual odometry system with the DVL-based system. The closer you get to the DVL-based system, the better. I'm finishing my time. So here you have the mean value of the error, visual odometry, DVL. And here you have a comparison of cost of the instrument and navigation performance. So the point of this slide is that actually you can compromise a little bit navigation performance, but saving quite an amount of money for the sensor. Of course, optical systems will work only in limited situations, while the DVL in bottom lock will work almost for any kind of bottom. Okay, I had here other images. Just a brief point on the fact that you can use visual odometry for hull inspection. We're trying to do that as well. We're going toward systems or comparing systems with stereo vision and laser systems. Laser systems are actually another payload that you want to have when you inspect a hull to correctly represent all the possible features that you may want to see on the hull of a system. I think I'm running out of time, so tracking, I will not talk about tracking, just to say that we have essentially, we have put together a system for tracking and comparing different navigational procedures. Here is a result in which we compare extended Kalman filter and unscented Kalman filter. And we use this tracking system also for estimation of dynamical model of the vehicles. Here is a result of a simplified model of the vehicle, prediction of speed, estimated speed in both cases, and the results are actually quite good, I would say. This is the team. Thanks for the attention, and I'm ready for questions. I will keep this sharing of the screen until the end of your questions, if that's okay for you.
Yeah, thank you so much, Andrea. Very, very interesting presentation. Also, we have a very similar problem, so I think many of us have found very interesting your presentation. So I understand essentially the key strategy for navigation is either collaboration among many vehicles or essentially using the payload in order to improve the navigation. Okay, yeah, so I have a question actually. So it is essentially which method is more suitable for very deep waters and very shallow water? And at this point, I read also the other question, which is what kind of visual features were used for visual odometry? And did you use PCL for frames stitching when mapping? I can give the priority to these two questions. Okay.
Okay.
Me, I will ask you later. Yeah.
Okay. So, what features? Actually, you can look at this slide that I picked up, not randomly, but because I did not insist much on this one during the presentation. This is for acoustic data, not for optical data, but the idea is the same. Actually, with acoustic data, is possibly more evident. That is, you can find features just by contrast in these images, and you navigate with respect to the features, okay, to the salient points. Then the stitching here is done with the navigation. So we are not trying to adjust the images, trying to look at features in the common features in different images and putting them together. We're looking at features during the navigation and rely on the navigation, which is based on the feature, however. Okay, so the stitching is done in this way.
Okay. Okay, thank you so much. Very interesting.
This possibly doesn't answer to the whole question before. In the optical navigation, optical navigation is done with a single camera, but again, the point is to measure the velocity with respect to the bottom. So again, you look at some salient features. In that case, from one. Okay, so essentially, this is. These are images in which you try to identify the same feature in one image and the next, and estimate it's almost an optical flow, if you like. And you see that there are some outliers as well, as you would expect in optical flow, in which you try to get one salient feature and see it in the next image, and from that getting the velocity. Okay, deep water, shallow water. Of course, optical systems or even forward-looking systems at low cost can be used in shallow water or very shallow water. In deep water, you will not see the seabed, either with a DVL, either with an optical system, or with a cheap acoustic systems. Okay, you may look at the seabed even at some distance, but to get to the necessary resolution, you will need quite an expensive sonar system to image the seabed. So in deep water, either you pay the cost of sophisticated onboard navigation systems that will drift anyway, That is, you may delay the drift, but you may not avoid the drift, or you have to go with a cooperative navigation with some surface asset to recalibrate your system every once in a while when communication arrives. The simplest cooperative system is the one with a surface vehicle and an underwater vehicle. But you may have a more complex system with just one surface vehicle and a networked transmission of information and achieve precision for all the elements, all the agents in the team.
Okay, so thank you again. I think anyway you are available through email for anyone who wants to make any question.
Absolutely, absolutely. Thanks, Julia. Thanks to the whole audience.